Hey folks, Mrs. White here. This is the first Move into Digital lesson that I'm putting together. As you can see, it looks a lot like if I was going to do a flipped lesson. I got my hands on a drawing tablet. It's a little old from Miss Mountcastle, so that I could still kind of conduct business as usual. So hopefully things feel familiar to you folks. I know this transition is going to be hard. It's hard for me. I don't have a whole big block of time because I have a 2-year-old at home. And I'll be recording these videos either during her nap time or after 8:30, 9 o'clock when she goes to bed. And so please be kind and be flexible. And I, in turn, will also make sure that I'm being as kind and as flexible as I can possibly be. So I want it to feel familiar. I want you to feel like you can reach out to me. Hopefully you've read the expectations document that was like quote unquote due today before this lesson. So if you haven't accessed that yet, please do so. Share it with your parents. And if you can, print and sign the last page of that PDF. If you can't print it, I'm perfectly fine with your parent just popping me an email. I have their emails on file saying that they've seen the paperwork and they're good to go. So today we're going to start off, or we would have started off with this problem right here. This is actually one of the problems from our exam we just finished, and it has to do with sample size. It was one of the ones people generally got wrong, but over the last week and a half or so, I've been trying to tie up loose ends with people who either need to finish these tests or were absent and hadn't even started them. Because of that, I don't feel comfortable going over this problem in a video. But I'm more than happy to. If you are feeling like this was one that was tricky for you, reach out to me. I can record going over this problem and send it to you independently. I just don't want to post it for the whole class. So today, since we're not going to go over this, we're going to jump right into section 11.1, right? Oop, see, not going to be very good at this. Okay, sorry. We're going to go over section 11.1. And what we're doing now is we're going to be looking at two samples, okay, as we compare populations. And specifically today, we're going to be looking at proportions. So our ratios, our percentages, okay? So how can we compare two samples from a population and specifically be comparing their proportions? So first things first, we're going to discuss independent versus dependent. We're also going to review qualitative and quantitative as it relates to variables and to data. We're going to review how do we do a distribution for first one sample for a proportion and then move into two. That's not like the real meat and potatoes. That's just kind of a review and an introduction to some of the really tricky calculations that your calculator would do. Then we're going to transition into hypothesis testing for two proportions, confidence interval for two proportions, and sample size for two proportions. So this sheet right here gives you an example for each of these items, these three things. So as we have our discussion about the distributions and about independent and dependent, that's not something that's going to be on the sheet, so I would encourage you to still have your notebook out if you have your hands on it. And hopefully everyone had an opportunity to get materials last week, either Monday or Friday. The homework assignment is these 4 problems. Those are the 4 I'm asking you to do because they're on the syllabus. I am going to add to it number 33. Because these do not include sample size, and 33 is going to give us an opportunity to practice this skill right here. So I did attach this to the homework. It is not a required piece. These 4 would be what you need to complete for Thursday when I release my next lesson. So if you could have those in before Thursday, that would be great. So Wednesday night at midnight. So let's hop into starting our discussion of Chapter 11. Specifically 11.1. So again, we're going to be looking at comparing two samples here, okay? And we're going to be comparing two samples proportions. So the percents or the amounts in each of those samples that cover some specific topic. Now, the calculations we do are going to vary depending on if we are dealing with a sample that is independent or a sample that is dependent. Okay, so I have an example of each here. So let's say we're talking acne cream. There's like a bunch of stuff that's supposedly really good for your skin or going to help you with problem skin, like proactive, I don't know, okay? But if we wanted to do some sort of hypothesis testing for comparing which medication works better, we could take two separate medications and apply them to the same face. And we would do the same face because that's going to help us have a consistent outcome, I guess. Like, you can't have a confounding variable if one of the unknown variables or lurking variables would be that different skin type, right? So let's say that we take medication A, this pink one, okay, and we randomly choose a selection, an area of the face to apply it to. So maybe we put forehead, cheeks, nose, and chin, those four areas of the face, on pieces of paper, put them in a hat, and pick one out. And we get chin. So we're going to apply our medicine A to the chin. On the same face, we're going to pick a different card out, and we're going to apply it to a different area, okay, because we can't apply medicine in the same space. Medicine B. So if you think about this, medicine A, since we said that that's going to go, I don't remember what I said, if I said chin or forehead, but let's say it's chin, okay? If medicine A is going to go on the chin, medicine B can't go there, so the opportunity of that being chosen, okay, is dependent on this, or is influenced by what happened here, okay? So there's only 3 options left in that hat. That means that this would be an example of a dependent sampling strategy. Okay, because what happens for medication B is directly influenced by what happened for medication A. And we'll see a couple more examples of that if it's still a little fuzzy. For independent, we could think of how much money you spend when you go for fast food. And I know that a lot of fast food places are still open right now, currently. So, you know, hitting up the drive-thru, if you have cash versus credit, does that influence how much money you're actually spending? So to do that, you would look at receipts from fast food places. You could look at 30 credit card receipts and 30 cash receipts. And if you think about this, the person in front of me, if they paid with a credit card, that doesn't change how I'm paying things, right? I'm not going to suddenly be like, oh, they paid with credit, I have to pay with cash, or vice versa, okay? Because this and this are 2 events that would happen independent from each other. This whole sampling would be independent, okay? And I always try to give these to you folks, the official definitions from the book. So let's take a quick second. These actually aren't too bad. A sampling method that is independent when an individual is selected from one sample does not dictate which individual is to be in a second sample. Okay, so it has no influence over the second sample, something that happened in the first. Okay, a sampling method would be considered dependent when an individual selected to be in one sample is used to determine the second sample. Okay, these are often referred to as matched pairs samples because what happens in the first dictates the second. It doesn't mean that they're 2 separate things, though, because an individual could be matched against themselves. Okay, so it's not like you have to have 2 totally separate entities, like a medication A and medication B. It could be a choice that a person makes, and then what happens because of that choice, kind of, okay? Like, what are the opportunities after that? So, along with independent and dependent, and hopefully right now you're feeling that that's familiar from Chapter 1, we also have categorical data. Nope, that's not what I wanted to put at all. We had qualitative data, which is like categorical. So qualitative, I spelled that wrong. I'm letting it go right now. Please be kind, and you can let it go too. And that's where we're looking at some sort of quality, or you could be looking at quantitative data. And in quantitative data, we're looking at quantity, or how much, how many. So what you'll look at for the next couple problems, we'll do 2 together, is this sampling strategy independent or dependent? And they're going to give it to us. Then we're going to be asked if the data that's being collected from each sample is qualitative, or describing a quality, or quantitative. And the reason why that matters, folks, is because qualitative data, okay, usually results in you working with proportions, okay, a percent of people that said this or did this. Quantitative data, okay, how much, how many, or comparing numbers, usually means that we're going to be working with, a mean of sorts. So that's, as we're moving forward, we know already that today 11.1 is going to be looking at proportions, right? So we know that we're going to be dealing with a lot of qualitative data, but we're going to at some point be having to make a decision. Are we dealing with qualitative because that's a proportion? Are we dealing with quantitative because that means we're going to be looking at a mean? Okay, and even though today we're going to focus on independent, at some point in this chapter we're going to see dependent also. So let's do a couple examples where we are identifying each of those. Oops. So we're going to decide whether it is first independent or dependent. We're going to look at the response variable, which is what we're measuring, and we're going to decide if that's qualitative or quantitative, and thus thinking about would we be looking at proportions or looking at means, okay? So our first one has Joliet Junior College deciding to implement a course redesign of its math program. The students are either enrolled in a traditional lecture format course or a lab-based, that's going to be fun, lab-based format, which lectures and homework are done on video. Okay, so kind of like what we're going to be doing, and the course management system, My Math Lab. There were 1,200 students enrolled in the traditional lecture and 300 in the lab. Once the course is ended, researchers determined whether the students passed the course with an A, B, C, or that they didn't pass it. The goal of the study was to determine whether the proportion of students who passed lab-based format exceeded that of lecture-based format. So if we're thinking, and we're not there yet, but kind of previewing, all right, what would we do for our hypothesis test here? They're saying that this would have to be bigger than this. Okay, so that would be one sample. That would be the other one. And our alternative hypothesis would be that this is greater than that. The null hypothesis is still going to be that the two things are equal. And we're focusing on passing, okay? We're not focusing, sorry about this, gosh golly, this is annoying. We're not focusing on the exact grade that they earned, okay? So that's important to know. So are we dealing first with an independent or dependent situation? Well, here, whether you're in this class or this class, it seems like if you're here, that doesn't influence this. So because this has no influence on our other sample, we would say that it is independent. And we're measuring grades, but we're not measuring actual percentage points. And in fact, we're not really measuring grades. We're measuring did they pass or did they not pass. So it's kind of like two categories, pass or not pass. So really, we're looking at qualitative data. We're measuring the qualitative. All right, you get what I'm saying. Qualitative data, we're measuring whether they passed or didn't. That's a quality. Okay, if we're dealing with qualitative data, right, we'd be dealing with a proportion, the percent of people that passed versus the percent of people that didn't, or comparing, in this instance, the percent of people who passed this and the percent of people who passed that, okay, a proportion. In this example, we're going to look at women. Do they tend to select a spouse who has an IQ higher than their own? So are women attracted to men who are smarter than them? To answer this question, researchers randomly selected 20 women and their husbands. So right now, I already know that it's going to be dependent because this happens randomly. This happens as a byproduct of this, if that makes sense. Okay, so this is definitely going to be dependent. We're looking at the IQ scores of each team and maybe even subtracting them to see the difference between them. Okay, so we could look at the average husband, the average wife, potentially separately, or we could look at the actual subtracted version of those, the difference of those, and see if it's positive or negative or what that number is. Okay, so IQ is how much IQ you have, and it's numerical, so it's quantitative. It's measuring a quantity. Okay, so we'd be dealing with averages there. So again, the average difference, the average husband, or the average wife, depending on what they asked us to do. So I want you folks to give this a try. I only gave you one homework problem for this, but you have to be kind of good at identifying it. So if you want to take a second and pause the video, read these over and decide which you think it would be, dependent or independent, and then qualitative or quantitative. So actually take a second and pause it because I'm going to go right over those answers in like 2 seconds. So let's go over the answers. I said it was going to be fast. And hopefully you kind of thought about this on your own. So here we're looking at how late teens and early 20s or mid-20s feel about Republicans and Democrats in Congress. That's going to be, if you read through the sampling strategy, it's dependent. Okay. And because we're looking at whether it was favorable or unfavorable, those are two categories. So they're two qualities. This would be qualitative. Okay. So we'd be looking at a proportion, a percent of people that said this, a percent of people that said that. Number 7, we're looking at whether a new curriculum is going to increase test scores. Okay. So she says she randomly divides her kids up. It doesn't matter. One group does not influence the other, so it would be considered independent. and we're measuring test scores. So this would be quantitative, which means we would probably, I'm probably going to spell it wrong. I'm just going to leave it. Okay. We would probably look at the means of each of those groups or the difference in means from each of those groups. 8. Here we are looking at, it's kind of like a interesting, if any of you are in AP Psych, this is kind of interesting to think about stimulus. So either how do you respond with a go, no-go, or a choice stimulus? The way the sampling was set up was in a dependent manner, and because they measured the amount of time for each of these responses, we're looking at the amount of time, so it's quantitative. Okay, and again, that means we would look towards the mean. This is what number 3 wants you to do. Think about dependent, independent, qualitative, or quantitative. Okay. So now that we have that kind of out of the way, I want to do a quick little review. It happens to be from Chapter 9. We used it again in Chapter 10. And it's looking at how do we do a sample proportion distribution. And a distribution has 3 parts to it. It has shape, it has center, and it has spread. And I'm hoping that as I say those things, you're like, duh, Miss White, I totally remember that. You might not remember all the pieces and parts, but that's what we're going to go over right now. So we're going over some old stuff. If we can do it with 1, right, a single sample proportion, we should be able to extend it to do it with 2. So to look at the shape, we want to determine if it's normally distributed. And so first things first, we ask ourselves, is it random? And I'm hoping that this feels like a super review. Next, because we're dealing with a proportion, okay, a proportion, we're going to do n times p times 1 minus p, and it's got to be greater than or equal to 10, okay? If it is, then it could potentially be normally distributed. The last piece is looking at your sample size, and it should be less than or equal to 5% of the, the population, okay? Because if there's population has a natural skew, if your sample size is smaller than 5%, that skew won't take over yet. So if those 3 things work, we can say that our shape is generally normally distributed, and we could continue with our work. To do the center of a proportion, okay, we have to find our mu of our p hat, okay, and p hat means sample proportion. So that is actually, your center is equivalent to what that proportion would be. So if we took our sample, we took our x value, and put it over our entire sample size and created that decimal and then changed it to a percent or just kept it as a decimal, that would give us our p hat, and p hat again is the same thing as the average of that sample proportion. Okay, p hat just means sample proportion. Next we have spread, and spread is generally standard deviation, but when we're dealing with a sample proportion, it has its own little calculation. So standard deviation of a sample proportion is going to be its own little formula. It is, since this has a P, the way I remember it, it's the big one, and it's going to have the P in it, okay? And hopefully this is familiar to you also, because this was covered in our last section. In fact, thinking back to the test, there was a handful of problems where you had to find the area to the left or the right, and a lot of you use normal CDF, but when you put in your center, you did this part right, but when you put in your spread, your standard deviation, you just put in either the original standard deviation or you did this calculation incorrectly. So remember, when we're dealing with a sample, your standard deviation, it has its own little calculation along with the center. So now that we have this idea down, we're going to expand it, and I'm going to show you what it looks like from the book. It's really messy. We are not doing these calculations by hand. So we're only going to briefly discuss the next slide. I do not want you to freak out about writing everything down. I just want you to see the type of calculations and maybe appreciate them a little bit before we just hop into using your graphing calculator. So, oops, went ahead 2. Well, went ahead like 4. Okay, so if we're looking at a sampling distribution for the difference between 2 proportions and we're dealing with an independent sample. So let's just take a look at what they put here. Suppose a simple random sample of size n1. 1 is delineating that it's the first sample, okay? It's taken from a population where x1 of the individuals have a specified characteristic. Okay, so x1 is how many people have whatever that characteristic is. And then this is your sample size from that first sample. And then a simple random sample size n2 is independently taken from a different population, okay, where X2 of the individuals have specified characteristics, okay? Again, different population because it's independent. Different population, it's independent, okay? So, the 2 delineates that it's from the second sample. The sampling distribution, again, we're looking at the differences. So it would be p hat of our first sample minus p hat of our second, where p hat of our first is x over n. And again, that's super similar to what we saw here, right? P hat is x over n. They just added the little ones to show it's coming from the first one. And p hat of 2 is the proportion for our second population, is approximately normal with a mean of p hat 1 minus p hat 2, so you would subtract the 2 to get the mean, with a standard deviation of this hot mess calculation, okay? So again, we're not going to stress out about that, but really, if you look, it's just the first one. Again, let's look at our standard deviation here, p 1 minus p over n. If we look back here, it's just p 1 minus p over n plus, okay, it's weird, I know we're doing a difference here, but we would add our standard deviations. The same for our second. After you sum those up, folks, and only after you've summed those up, would you square root it, okay? And you can only take these calculations, this center and this spread, provided that both of them have an n times p times 1 minus p, okay, from our first sample and our second, it has to be greater than 10, that neither sample size is greater than 5% of the population, and that you could do this calculation for the z-score. Again, we are not going to stress out about finding the z-score. You do need to know that z-score, though, is your test statistic, which is the same test statistic that we use for our other proportions, right? But our z-score is just going to be calculated differently. It's going to be, you're not going to have to do it by hand, so we're not going to stress out. I don't want to make this video longer than it needs to. Okay, but your test statistic when you're dealing with a proportion, regardless if it's 1 or 2, is always going to be your z-score. So, keeping those ideas in mind, okay, and that they are related to what we've done in the past, let's look at doing hypothesis testing now, okay? And we're going to look at 2 population proportions, okay, and compare the 2. So, at this point, if you want to make sure to grab that worksheet I have online, or if you wanted to at least reference it, it has the same word problem on it. You could print it out. It's on one whole side of that sheet. It's up to you. So let's take a look at this problem. In clinical trials of Nasonex, this many adults and adolescent allergy patients were randomly divided into 2 groups. Okay, so they're saying they were randomly divided into 2 groups. I right now know that this is going to be independent. Okay, it's important to keep that in mind, that it is going to be independent, because that's going to dictate my next set of steps. The patients in group 1 received Nasonex. The patients in group 2 received a placebo. Of the 2,103 patients that were in the experimental group, meaning they got the medicine, 547 had headaches as a side effect, or reported headaches as a side effect. Of the 1,671 patients that were in the control group, 368 reported headaches as a side effect. Is there significant evidence to conclude that the proportion, so they're telling us we're going to do a proportion, okay, of Nasonex users who experienced headaches as a side effect is greater, okay, than that of the proportion of the control group at a 0.05 level of significance, okay? So just because it makes sense to me right now, I'm going to write out my null and my alternative. So again, null, we write like this, okay? If I look at this, they're saying users who experienced headaches. So that's my experimental group. Just to the side, I'm going to make my experimental group my P1. Okay. So the idea with our null is that it's always going to be equal. That means there's no change. There's no difference between the groups. Okay. My alternative hypothesis, and again, it could have a 1 here, it could have an A, is that those who, we'll put a little P2 here. Okay. Those who experienced headaches that had taken Nasonex, so our experimental group P1, is greater than the control group, so is greater than my control group. Okay, this is my alternative hypothesis. It's what I'm trying to prove, okay, or disprove or provide evidence for. Remember, it's not really proof, it's that do we have enough evidence or not, okay? It's really not anything factual. We're just seeing, is our information significant enough? So We are clearly given 2 samples. It seems silly to ask that, but when we get into chapter 12, we're going to be dealing with more than 2 samples. Okay, so we started with 1 sample. This whole chapter is going to focus on 2. The last chapter that we do this year is going to look at more than 2. So, first things first, we need to determine our 3 things for normality. Okay, if it's not normal, we can't do anything. We're going to ask ourselves, is it random and independent? Yes, it's random. Yes, we already talked about how it's independent. We have to check and see if both of these sample groups here and here are, if I do my n times p times 1 minus p, if they are going to be greater than or equal to 10. So this is actually going to be 2 pieces of work here. So I'm going to start off with my experimental group. This is going to require a little bit of work. I'm going to do my n, which this says experimental, so it's 2103 times my p. Now I don't have a p-value here. I can come over here and do it. My sample proportion for my first sample is going to be my x over n, and our x value here is 547 over my n, which again is 2103. So I should grab a calculator, do some division, and I'm going to get, hopefully you have a calculator with you too and you're doing this along with me, 0.26, and we'll just round to the 0 there. Okay, so 0.260. So that means I'll put 0.26 here. And then my 1 minus p is going to be, let's see, 25, 26, so it's going to be 0.74. And I want to make sure that is greater than or equal to 10. And if I multiply all these together, okay, I'm going to get something a lot larger than 10. Okay, take a second and multiply that through. I'm just going to try to save some time right now. Our next one, I have to check my control group, okay? And their n value was 1,671. I do not have my p-value for that one, so I'm going to do my sample proportion from my second sample. I'm going to take my 368, and I'm going to divide it by 1671. So if I were to do that on a calculator, I'll go out 3 places again. It's going to be 0.220. So over here, my n times p times 1 minus p, so that's going to be 78, so 0.78, must be greater than or equal to 10. Again, because this sample size is so big, I know I'm going to be good to go there. So it's random and independent. Everything is, when I multiply it out, is greater than or equal to 10. And now I want to look, is this less, both of these even, or they're combined, it doesn't even matter. Is that going to be less than 5%? I mean, heck yeah, there's a lot of people, okay, that have allergies, and that's what we're looking at is adult and adolescent allergy patients in general. So I would say that, yes, it is less than 5% of my population size. That's our capital N. So since this is good, okay, I've already outlined my null and alternative just because I was feeling it. Okay, I did that first. I should outline my alpha, which is 0.05. Okay. And now I'm ready to start doing some calculations for this, okay? And we're going to focus, like I said, on using our calculator really as kind of our basis for all of our calculations. We aren't even going to do the test statistic by hand. What's nice here is that everything is going to start feeling very familiar. If this should have felt familiar, this should have felt somewhat familiar, even though now we're dealing with P1 and P2, okay? Classical should feel familiar. P-value should feel familiar. Really quickly, I want to think of what our curve would look like. I'm looking at this being greater than this, so I'm really looking at a right-tailed part of my graph, okay? So let's go over, we're going to do p-value first. For p-value, we do what we've kind of already done in the past. We're going to do stats on our calculator. We're going to go to tests. And then we're going to go down to option 6. And I want to talk to you about what this name is. It is 2, and then it says prop, and then it says z, and then it says test. So 2 means that we're dealing with 2 samples. We're dealing with a proportion. We're dealing with z-score because we're dealing with proportions, and we're testing our hypothesis, okay? The 2 is 2 samples. The option we did before this was just number 5. It was one prop z-test because we had one sample. So if you were wondering about the 1 or the 2 previously, now you know, okay? So I actually have a free trial of this app. So we'll clear out of this. Let's go stat. Let's go over to test. That's fun. Let's go down to prop z-test, right? And then what do we have to plug in here? So we have an X1, X1, N1, and X2, N2 are just your raw data, okay? People that were in the group of your first sample out of the sample size. People that were in your group that you wanted from the second sample over your sample size. And then literally this is just like what we had before, okay? And then we would click calculate. So I got to pull that information. Actually, I don't. I have it in my notes right here. For X1, I'm going to put in 547. Whoa, that is not what I wanted it to do. Let's try again. 547. I'm going to go down. My sample size here was 2,103. Oh my gosh. 2103. My X2 is going to be 368. And the sample size of my X2, or my second sample, excuse me, was 1,671. 1,670. 1,671. Okay. And then if we look at our alternative hypothesis that we did come up with, we chose, I don't even remember, and I didn't write that down. We said that P1 has to be greater than P2. So if we go back to our calculator, P1 has to be greater than P2. So I'm going to go down, over, press enter, and then down, calculate. Woo! Now that screen should look familiar. We have Z for our Z-score. That is our test statistic. So if we're here and we're wondering what our test statistic is, test stat. It is 2.8393. Okay. Next, we would look at our p-value. And this is the one that we're going to compare to our alpha. Our p-value here is 0.00226, so we're going to do 0.0023. 0.0023. So we're going to take our p-value now, and we're going to ask ourselves, is this smaller than our alpha? And I want to remind you, your alpha, your level of significance, is the probability of having an error. So is this smaller than the probability of having an error? The answer here is yes, it is. This is true. That means, since this is smaller than our potential for an error, we do have enough evidence, okay? So our conclusion here would be that there is enough evidence at a 0.05 level of significance to say that those people in the experimental group did have more headaches as a side effect than those that were in the control group. Okay, that would be my general conclusion for that. I would not just say, that you reject the null. All right, you have to write it all out as we always have. Now for the classical method, you need to first have your test statistic. We are not going to calculate this by hand. In the past we have. We're just going to look over here from what we got from our calculator. Okay, we're going to simplify our lives a little bit. It's 2.8393. 2.8393. Then we're going to think of our curve again. Let me make this full screen real quick. Okay, I'm looking at the right-tailed here. I need to figure out what is the z-score that corresponds to this alpha right here, okay, this 0.05. Now, if it was two-tailed, I would have to do z-score of 0.05 divided by 2, but I don't have to worry about that. If it was over here, I would put negative z of 0.05, right, because it's to the left of our average, and that's how z-scores work. So how do I figure out this z of 0.05? I go to the back of my book. And in the back of my book, I go to the z-score table, at the very bottom of it, and I don't think I have it open here, at the very bottom of that table, it says hypothesis testing, and I would see that if I have a z-score of 0.05 and it is right-tailed, my z-score is going to be 1.645, okay? So now I'm going to look at where does this test statistic fall in relation to this. So 2.8, if this is 1.6, 2.8 is here. It happens to be in the shaded region. If it's in it, okay, that means that there is enough enough evidence to reject the null and accept the alternative, right? There is enough evidence to say that this is true. So again, it would have the same conclusion. We would say there is enough evidence at a 0.05 level of significance to say that those who are in the experimental group experienced greater headaches than those who were in the control group. Boom. Very, very similar to what we've done, just a different keystroke if we're looking at doing p-value, okay? But everything here, once you have this test statistic from this calculation, this is exactly the same as what we've done in the past. So hopefully after seeing this, it's a little bit more familiar than it was before. Let's move on to looking at a confidence interval, okay? I only did one example of each, and then your homework has two hypothesis testing ones, numbers 9 and 17, and then it also has a confidence interval one also. So if you flip over your note sheet, we'll take a look at this problem. Again, we're going to be dealing intentionally with 2 samples because we're doing that right now in this chapter, but moving forward, we're going to see where there's more than 2. So the Gallup organization surveyed 1,100 adult Americans in May of 2002. Then they conducted another one in 2014, same amount of people each time. In both surveys, they asked the following: right now, do you think the state of moral values in the country as a whole is getting better or worse? So in 2014, 816 of them said that they think they're getting worse. In 2002, fewer people, right, 737, said that they think that it's getting worse. So that number did go down, but is it enough to say that it's significant, right? Is it statistically significant or not? So it says construct, and we're not actually doing a hypothesis test here, okay? But I want to make that clear. We're not doing a hypothesis test. It's telling us to construct and interpret a 90% confidence interval for the difference between the 2 population proportions, okay? So it does tell us that there's 2 proportions here, 2 samples, and that we're going to be doing a confidence interval. Now, just as before, we still have to check our 3 important things, okay? Is it random? Yes, they said they were randomly surveyed, okay? Is it independent? So does this people from 2002 influence 2014? And the answer there is no, it's definitely independent, okay? We can think of our data that we're collecting here. Again, if we kind of want to tie that back in, we're looking at, do they think that it's worse or better? Those are clearly categories. That would be a qualitative data. In qualitative data, we would look at proportions. Okay, so it kind of all ties in why we're looking at proportions for these. Okay, percents, proportions. Next, we would have to do our n times p times 1 minus p for each. Okay, and make sure that it is greater than or equal to 10. And remember, I need to do that for my sample proportion for 1 and my sample proportion for 2. I'm not going to calculate these, folks, right now. They do both work. I'm just, again, trying to save time so these videos aren't stupid long. And both of the samples, right, 1,100 adult Americans, there's way more adult Americans than that. That's clearly less than or equal to 5% of Americans. Okay, very, very small percentage of Americans. So we can say that it's generally normally distributed. It's 2 samples. Now we're ready to start doing some work here. Now, a confidence interval, at one point we discussed how to do it by hand. We don't need to do it by hand. You're not going to do it by hand. So let's talk about the keystrokes. You're going to go stats. You're going to go test. So a very familiar menu. Once you're in there, you're going to scroll way down to option B, which is 2 prop Z int. Let's talk about this name. 2, because we're dealing with 2 samples. Prop, because we're dealing with proportions. Z, because that would be our test statistic. And interval, because we are finding a confidence interval. Okay? So, keep this, well, write down these numbers really quick on your sheet. 816 over 1,100, 737 over 1,100. That way when we take a look at our calculator, it will make more sense. So, oh, I should just keep that open, actually. I can do this. Boom. All right, so we're going to go stat. We're going to go over to test, okay? Once we're, oops, that's not what I want to do. We're going to go stat. We're going to go over to tests. We are not going to press enter. We're going to go down again to option B. It's really far down here. And again, 2 because we're 2 populations, prop because we're dealing with proportions, z because that's our test statistic, and int because we're doing an interval, okay? And there I'm going to press enter. And it asks us for the same information, okay? How many people have that chosen attribute out of how many in your first sample, how many in the second, how many out of everybody in your second. So here we have, let's see, our x1 would be 816, and our n1 would be 1,100, and our x2 is going to be 737, and our n2 is going to be 1,100. And our confidence interval here is actually going to be 0.90, right? Because they wanted a 90% confidence interval. And we can just come over to enter now. And there we go. Okay, here's the interval in which that occurs. And that's what I should write down. So I have it. You can take a second, actually write it down. It is 0.0396, comma, 0.10368. Close it up. Now, I'm not going to write this all out because it's going to take me forever to try to write it out online, but there is a specific way that we should interpret this, right? Okay. We found the interval. The way we interpret it is we would say that we are 90% confident that the difference between, okay, because we're looking at what happened from 2002 to 2014, that the difference between the proportion of adult Americans who believe that moral values are getting worse between 2014 and 22 is between 0.0, sorry, I'm like zoning out, sorry, 0.0, we'll round that up, 4, to 0.10, okay? We also could interpret this as it being an increase, right? So from here, or excuse me, from here to here, okay, it was a 4% increase or a 10.4% increase. So I think I kind of didn't discuss with you how to determine which one is X2 and X1. So let's take a closer look to this. I did it in my notes, but I didn't talk you through it. So you're like, why did you plug in 816 for X1? Well, 816 is the most recent one. So if we're looking at how things changed, we take kind of like the current, right, what is currently happening, and we would subtract the old stuff from it. And that would tell us if things went up or down, okay? So if we look here, and I think I kind of messed this up a little bit, currently would be this, okay? Past would be this, and I flip-flopped it when I said that. So that increase from here to here, we can be 90% confident that the increase is between about 4% to 10%, okay, of people now increased in feeling that the moral code of our country is getting worse, okay? Sorry about that confusion. If you're still a little fuzzy on that, feel free to give it a go in your homework problems, and then if you need to, stop in for my office hours on Wednesday, and we can make that work. Okay, sorry about that if it was a little funky. So let's go to our last thing here is going to be looking at sample size. And this was a piece, folks, that maybe we didn't get a whole lot of practice on. It wasn't in the quiz a lot for Chapter 10, but it is something we need to make sure we're covering in Chapter 11, so you want to make sure that you're paying attention to it moving forward. Okay, if this is a section we're covering, it's free game on a quiz, it's free game on that Chapter 11 test we're going to take. So just like before, there's 2 instances. This is the formula that we would use, okay, if we are given prior information, okay? Similarly, this is the equation we would use to figure out sample size if we are not given any prior information. And if you look, this whole last step from here to here is identical, okay? They just add the 0.05, just saying that like the odds are 50-50, okay? Because we don't have something to previously look at. So we're going to use both of these formulas. Take a second, write them down, and we'll use them each in the next example. So a nutritionist wants to estimate the difference between the proportion of males and females who consume the USDA's recommended daily intake of calcium. What sample size should be obtained? So they're asking us for the sample size. We don't just wing it. There's a calculation. Should be obtained if she wishes to estimate within 3% points within a 95% confidence, assuming that this and this, okay? So in A, they're giving us more information, and in B, they're not. Okay, so we're going to actually use each formula here. So in A, she uses results from a previous experiment, okay, where they found out that 51% of males and 75% of females do consume the recommended daily intake. Here, there's no prior estimates, okay? So we're going to go look at our formulas. Let's start off with this part A. Our formula is going to be the population proportion from our first sample times 1 minus that. And then we're going to take that and we're going to add to it the other exact same thing from our second sample. So we're going to do our proportion from our second sample times 1 minus that. And then once we get that number, okay, so we'll get that whole thing down. We're going to take that and we're going to times it by, and this piece stays the same in both, the z-score of our alpha divided by 2 all over our margin of error, and this should be in parentheses. Once you find that number, you square it, okay? And that's going to give us the amount of people we would have to ask, and you need to make sure that every time, and I'm saying this because some of you didn't do it on the test, and I did not mark you down this time, every time you have to round up. You do not round appropriately, you always round up because it's the minimum amount of people you need, okay? So, if we look here, we could say they gave us males and then females, so we could take, and we're adding this, so the order doesn't really matter if this is males and this is females, or this is females and this is males, right? In addition, the order doesn't matter at all. So, my p hat here is 0.511 if I'm dealing with males, because they gave me that. If I subtract that from 1, I'm going to get 0.489. I'm going to multiply those two things together, right, to get this one little chunk, and that's going to give me 0.249879. Now, we really shouldn't, if you're using a calculator, you shouldn't round it till one of the last steps, because if you round it in one of the early steps, it's really going to influence the outcome, okay? So let's come over to the second one. We'll look at the women's data. So 75.2%, so 0.752 times, I'm going to subtract that from 1 and get 0.248. I'm going to multiply those two together so that I can add it, and it's going to be 0.186496. Ooh, sorry about that. If I sum those two up, I'm going to end up with 0.4364. We'll just round that. 4364. And then you're like, well, how do I do this? Well, our alpha is always the opposite of your level of confidence, right? If I'm 95% confident, that means there's 5% that could be a margin of error. Not margin of error. 5% where there could be an error. Margin of error is this 3%, okay? There could be an error. We have a symbol for a type 1 error. It's alpha, okay? Remember, that's the probability of having a type 1 error. So to get alpha, we just do 100 minus 95. So this is going to be 0.05 over 2. And honestly, folks, what you should do at this point, once you figure out what this margin of error is, you should go to the back of your book to table 5, which is the z-score stuff. And if you look at the bottom left corner, it's going to say confidence intervals, or it's going to say yeah, it does. It says something like that at the very bottom left corner, okay? So you'll look up this whole situation. It's going to say 1.96, okay? And you're going to put it over our margin of error, which is 3%, so 0.03, not just 3%, because everything here is proportions, and then I'm going to square it. So I'm going to divide these out, okay? I get, let's see, 65.3 repeating. I'm going to take that number now and I'm going to square it. And I'm going to get 4,268.4 repeating. And I'm still not done because now I got to take that number and I got to times it by 0.4364. Okay. Once I multiply those two together, I'm going to end up with 1,862.74. And I always round that up, so 18,063 people. Again, you have to use a calculation here. You can't just be like, I don't know, 1,000 people, 200 people. You have to do this calculation. And if you have prior information, you take your P and your 1 minus P and you add it to the P and the 1 minus P from the other sample. Once you find that sum, you do this little mini calculation here. Okay, and this little mini calculation is what we're going to use on this. Here they did not give us a prior estimate. So I have 0.5, and I'm going to times it by the z-score of my alpha divided by 2, all over my margin of error, squared. Okay, I already know my z-score of my alpha, and again, alpha is going to be 1 minus your confidence. Okay, that's your probability of making a type 1 error. So that's going to be 0.05 here. So I'm going to get that same number. I already got it for this one. It was 1.96. So I have 0.5 times 1.96 over 0.03 squared. And this whole chunk I did over here, right? Ended up getting a 65.3 repeating when I divided it, and then when I squared it, I got this 4,000. So I'm really going to have 0.5 times 4,268.4. Really, I'm just halving that. So I end up with 2,134.2. And I have to round up. Okay, it doesn't matter if this is a 0.2 and I should round down. I always have to round up because I have to have this covered in my minimum. So it's going to be 2,135 people. Okay. So this section covered a lot. It started out, if we look, let's just do a quick little summary of what was covered. And then I'll let you guys get going on your homework. You have 2 days to complete it. So we looked at 2 population proportions, determining if it's independent or dependent. And then we also reviewed qualitative and quantitative. Okay, and that's going to be something you're going to see in your homework. Then we talked about our old school distributions that we had done in Chapter 9 and looked at what the calculations would be for doing it with 2 proportions. They're pretty complicated, so we hopped right to using our calculator to do all the things we needed to do. So we did hypothesis testing, remembering that we use P1 and P2 to delineate our first and second sample. But otherwise, we checked pretty much all of the same stuff. The keystrokes are a little different because we're dealing with 2 samples again, but it's still a prop Z test, so 2 prop Z test. Our p-value we still compare as less than. We want it to be less than our level of significance in order to accept the alternative, which we did do here. We accepted this and we rejected the null. Then we looked at doing a confidence interval. So I outlined how many samples there are every time, 2. Okay, that's going to be the answer for this entire chapter. Is it normally distributed? Our answer was yes. Okay. And here we needed to think, okay, what's going to be our x1 and our n1 and our x2 and our n2? Well, we wanted our x1s to be the current information because we wanted to see if it had changed since the past, okay? So our current information, which is right here, we can tell actually went up from here. So that's why these numbers are positive, because they went up. It was about a 4. We are 90% confident that there was between a 4 and 10% increase in the amount of people who felt that the moral values of this country is getting worse. Okay. Then the last piece we did is we looked at how to determine sample size given 2 proportions. How many people should we ask? Okay. And if you're given information, we kind of do this long equation that looks at our p and our 1 minus p, summing it up for both, and then timesing it. Or if you're not given that information, it's a little simplified. You just do 0.5 times that same little equation there. Remember, this piece right here, you're going to use information on the back in the back of your book at the bottom of table 5. Okay, that's how you're going to get this number. If you need access to the back of the book materials and you don't have it on paper, it is on my old homework website. I can also make it available under this link too. Okay, so that you can make sure to have that digitally. So your homework assignment is those 4 problems, number 3, number 9, number 17, and number 21, with an optional problem 33, which has you looking at sample sizes like we did in this last example. Okay, and that again is on page 533 of your book. If you do not have your book with you, I have attached a Google Doc that just has screenshots of those 5 problems. You only have to do 3, 9, 17, and 21 though, because those were the ones outlined by UMA. So if any of this is tricky, I really want you to try your homework maybe tomorrow, spend like half hour at the most on it. And if you're stuck, then maybe on Wednesday when I hold office hours, and I'll put out a note on Google Classroom what time makes sense for you. I can do them generally whenever, but depending on it, you're going to have my daughter like screaming in the background. So I would prefer it be between 12:30 to 1:30 or probably 1 to 2 would be best. So I'll put out feelers if 1 to 2 will work for you folks for office hours every day. And hopefully that does jive and you guys aren't like working jobs right now that require you to be there. If not, you can always send me an email. I got to end this video. It's getting long. I will touch base with you folks later. Reach out if you need to. Bye.